Good evening. So the in the lectures that we had covered until now, we were talking about the position control of the end effector of a robotic manipulator. Okay. However, that is not the only way. That may not be the only type of tasks that that a manipulator may need to perform. Okay, so in the control, as I said earlier, in the control strategies that we had seen until now, like the PD control or the inverse dynamics based control, what was done is that the what was happening is that the manipulator is not interacting significantly with with the environment in which it is working. So the manipulator is just moving in the environment. It is not actually interacting too much with the environment. So that is like you have material transport or you have a pick and place operation. Okay. But there may be situations where you would require the manipulator to interact with the environment, that is apply force against the some environment. Say for example, you take a case of a manipulator or a robotic arm that is cleaning a window. So you have a sponge here and some amount of force has to be applied onto the window, and the manipulator has to move in this xy direction. Okay, so the point is that we are not so much interested in what is the what is the z position of the manipulator. What we are interested in the z direction, some force, some particular force has to be applied, so that can translate to enough number of enough amount of force so that the cleaning operation can happen properly. Okay, and the feedback now that is required is in addition to only the position information about of the joints of the manipulator, we also would add in the position of the measurement of the amount of force that is applied along the z direction. Okay, so now what we are dealing with is we want to try to control the forces of the interaction between the manipulator and the environment. That is why we are calling this as force control techniques. Okay, so since we are talking about measurement of force, there can be various type of sensors that can be used for the measurement of force. So there may be sensors in the wrist of the manipulator, which will or there may be sensors in the joint of the manipulator. So if you have a wrist manipulator, there may be array of strain gauges, something like this. This is a 6 degree of freedom strain gauge. Okay, so it can detect forces in three direction, torques in three along about three axes. So it can, by slight deflection of the strain gauge, you can measure the amount of force that is applied in x direction or in y direction or in the z direction, and similarly the torques that are experienced by this wrist about these three xyz axes also. You can also have joint torque sensors, which will be they are sensors that are embedded within the shaft of the motor of the actuator actually. So, and you also have tactile sensors. You may also have a tactile sensors, which are basically sensors at, so if you have a gripper like this, these sensors will know whether you are touching an object or whether you are not touching an object, and if you are touching, with how much pressure, the amount of pressure that you have put on that object. So this is more with whether a firm grip has been achieved or if the grip is too tight or whether it is too feeble. Okay, that can be achieved, that can be sort of measured using the tactile sensors. Okay, and in most operations, where the operation is free, that you can have multiple tasks to be done. They six axis wrist sensors, that is like something like this, that is being used with where there are six strain gauges in different directions. Okay, now what is happening when the manipulator comes in contact with the environment? So it is when there is a boundary which the manipulator cannot freely move across, a boundary that will give a resistance to the motion of the manipulator. First of all, let us assume the simplest case, that you have a manipulator that is completely rigid and a boundary, an environment, okay, an environment that is also rigid. So you have a manipulator that is rigid and the environment also being rigid. So when this contact happens, now what is happening is that the manipulator can no longer move in this direction, in this particular direction. Okay, so it loses 1 degree of freedom. Okay, however, it can now exert a force on the environment, against the environment. Okay, earlier the manipulator exerting a force was not taken into consideration at all. That was not a point at all. The motion of the manipulator was what was concentrated upon. Now in this case, we are concentrating on the amount of force that is being applied in any particular direction. Okay, so to quantify what is the motion and also the forces that are experienced by the environment and also by the manipulator, we bring in certain mathematical ideas. We bring in the ideas of screws. So the screws are six-dimensional elements, six-dimensional vector spaces. Okay, and the screws, they can be based on motion or based on force. Okay, so the motion based, the velocity based screws are called as twists, and they, as I said earlier, they are six-dimensional vectors. So you have velocity in three directions and angular velocity in three directions as the elements of this twist V. And similarly, you also have instantaneous force and moment based screws, which are called as wrenches. Again, you have three linear forces and three angular moments. Okay. Okay. Now, since we are talking about a six-dimensional vector space, the motion space and the force space both have six basis elements, and these two basis sets are said to be reciprocal, provided these set of relationships are obeyed. That is, you have arranged E1 to E6 and F1 to F6 in this direction, such that EIFJ is equal to 0 for I not equal to j, and of course EIFI is equal to 1 for I being equal to 1 to 6. Okay, so in the sense that in some sense, if I arrange it in this manner, that is, if I write it like E1 transpose E2 transpose and E6 transpose, and write this as F1 F2 up to F6, this product will be an identity matrix. So in some sense, this set of vectors and this set of vectors are in some sense reciprocal to one another. Okay, and we are saying that the basis set is reciprocal. That's why you say that these two set of basis vectors are reciprocals to one another. provided these conditions are being satisfied. Okay, now when you're talking about this reciprocal basis, then we can define the product of the velocity and force vectors. That is, the dot product v dot f is v transpose f. That is, the velocities being coupled with the forces and the angular velocity is being coupled with the moments. In this manner, in this mathematical equation. Okay, the advantage here is that when you know that you have reciprocal vectors, okay, you have two sets. You have v and f, the v and f in a manner that they are part of a reciprocal set of bases. Then if I change the units of one of them, the reciprocal the condition of reciprocity doesn't change. That is, in a sense, what I am saying is that if you have the vectors e1 to e6 and f1 to f6, then uh, the condition of ei dot fi fj, that doesn't change even if you scale one of those vectors. Okay, so let me sort of clarify this in a more this fashion. Okay, uh, so what we are saying is that if you have the vector v and f such that v dot f is equal to 0, if I change the basis for v, that is, instead of using e1 to ef e6, you use some alpha e1 to alpha e6, where alpha is a scalar. There is a linear change in the basis that will not change the way your the v dot f happens. If v dot f was 0 with this basis, even if I change the coordinates by a linear change in coordinate, by using a linearly scaled version of these basis vectors, then too the orthogonality condition doesn't change. So this is v transpose f here. Okay, however, the same cannot be said about orthogonality of v1 dot to v2 or f1 to f2. The reason for that is when you are writing v1 transpose v2, you are writing about this. So these two things are actually actually this expression itself doesn't make sense, and mathematically this expression is not invariant with respect to change of basis scaling. So if you have, so let us say, even if you have, say, v1 into something like, so if you have v1 and omega 1, and you have v2 and omega 2 as a basis vector, and if you say that v1 v2 plus omega 1 omega, so v1 v2 v1 transpose v2 omega 1 transpose omega 2, if this was 0, now if we scale v1, the velocity part, if you scale the linear velocity part, if you scale, what you end up with, if this was 0, now you can't say that alpha v1 transpose alpha v2 plus omega 1 transpose omega 2 is equal to 0. This statement now cannot be made. So the linear change in basis is not invariant. So if the linear change in basis being not invariant, what you're saying is that the orthogonality is not invariant to the change of basis of the reciprocal basis. Okay, and in a more basic sense, what this all means is that this sort of an expression doesn't really make sense. because these, when you say when you say that v transpose f, a velocity into force or a uh, angular velocity into movement, they make sense. But a velocity into velocity and a angular velocity times an angular velocity, they do not, they are not actually the same units even. Okay, so this summation itself is something that is ambiguous. Okay, as I said, that the linear coordinate and angular coordinate can't really be orthogonal to one another. Okay, so what we want to do is that we want to change the way this can be done. So to explain about the axis being the orthogonality condition not make any sense, you are expressing two vectors in the same. So in the first case, you have the angular component being written in radians per second and the velocity component is being written in meters per second. Okay. In the second case, I am using a linear change in basis. So instead of using meters per second for the velocity, for the linear velocity, I am writing it in terms of centimeters per second. And V2 again, and the angular component is anyway radians per second. Okay. So what is happening is that I am basically using the same vector. It's not, I'm not changing the vector. I've just scaled the vectors representing it in a different unit. Okay. So in the first case, you would see that if you do V1 transpose V2 with these numerical values, you would get V1 transpose V2 is 0. But in this case, it is not 0. So we have, even though basically the vectors have not changed, the orthogonality condition seems to have lost. Okay, and to address this issue, we have this uh, concept of a Klein form and a Killing form, where the Klein form is defined in this manner. That is, if you have V1 and V2, then this is V1 transpose omega 2 and omega 1 transpose V2, and the Killing form is just the angular velocity components being taken as a dot product. Okay, and for the above example, if you solve the above example, you would see that irrespective of a linear change in basis, even with a linear change in basis, the orthogonality condition remains if you define orthogonality using this thing. And the notation also makes sense. Say, for example, if you take the Killing form, it just, this being equal to 0 means that the axis of rotation of both these the axis of rotation in the two cases is actually orthogonal to one another. Okay, and at the start of the lecture, we were uh, working on the concept that when a manipulator is interacting with a environment, what is happening is that there are some direction in which velocity is restricted and there are some direction in which force can now be applied. Okay, and because of this, you say that some constraints arise, and you can you can quantize means you can quantify those constraints as natural constraints and artificial constraints. So natural constraints are those constraints which arise when the which arise from the environment itself. Okay, and artificial constraints are those constraints that arise due to the desired trajectory or desired application that is there. So the natural constraints arise from the reciprocity condition, and artificial constraint is used to define the reference input for the motion and force control tasks. And when you're talking about constraints and when you're talking about these velocities and forces, we have to have a reference frame with respect to which all these vectors are being defined. And that reference frame is usually the constraint or the compliance frame, which is the frame in which all these specifications and all the constraints can be easily expressed. For example, let's go back to the window pane case. Here, if you say that if you set the axis in a manner such that the window, the surface of the window is the xy plane, and the direction perpendicular to the normal to the surface of the window is a z plane, or let us say xc, yc and zc plane, then what you have here is that you have no restriction of motion in x direction or y direction. However, there is restriction of motion in the z direction. You can't move in the z direction. And however, a force can be applied in the z direction. Okay, so the constraint that there is no motion in the z direction, so Vz being equal to 0 forms a natural constraint, and the ability to apply a force in the z direction, the desired force in the z direction, let us say Fz is something, okay, some particular value, will be the artificial constraint. Okay, let's take another example. So here in this example, what you have here is that you want to move the peg into a hole. Okay, so now what the natural constraints are that the peg cannot move in the y direction or in the x direction. Okay, so the velocity along x and z direction, x and y direction would be 0. And since there is nothing to impede the motion of the peg, there is no force in the z direction, no force or movement along the z direction. Okay, so those would form the natural constraints because they do not depend upon what is the task at hand. Now, the artificial constraints are those constraints that depend upon the torque at hand. Okay, now what the task at hand is to move this peg into this hole, but at the same time you don't want any force to be applied in the x direction or in the z direction. So you need to move with a velocity Vd along zc axis, and you should not apply any force along the xc or yc direction, and you should not cause any movement about the xc or yc axis. So there should not be any twist in this direction also. Okay, there should not be any attempt to twist in this direction. An attempt to twist may not cause any motion, but it will definitely cause a force. And in addition to this, I don't want to rotate the peg also in the zc direction. So if you write it in terms of the constraints, okay, you would get this case. Okay, let's say that let take the dot product of v dot f and then see what happens. Okay, so you have the compliance frame as xc yc zc, oc xc yc zc, and you have the constraint that you cannot move in xc or yc direction, you cannot rotate about xc or yc axis, and there is no force about the along the zc axis. So that would turn out to give you 6 natural constraints from the velocity, from the lack of velocity actually, from the lack of linear velocity or angular velocity, and from the lack of force along the zc axis or moment about the zc axis. Okay, so those are the natural constraints that you have. And what about the actual artificial constraints? So you should not apply any force along the x-axis or along the y-axis, nor should there be any movement about the x-axis or the y-axis, the peg should move with a velocity vd along the zc axis, and there should not be any rotation also. So those are the 6 artificial constraints. So when you put all of them together, when you put these conditions together, you see that v transpose f is equal to 0 in this case. Okay, so what you have is that in the ideal case, when what the main point is that we have ignored one or two major factors that are usually present in any environment. One point is that an environment can give a resistance to, so an environment can give resistance to motion, that is, there can be some sort of a friction in the environment, or the environment can be a bit compliant to the force also. So it's not completely rigid also. Okay, so practically, but in practical cases, contrary to the claim, or in practical cases, contrary to the assumption that there is no friction and perfect rigidity of both the robot and the manipulator, there is some compliance, and the other condition that we have assumed was that if there is a force applied in this direction, there is no motion in this direction. Okay, but in practical cases, the compliance will exist, so the environment can get slightly deformed, as the case is shown here, with respect in response to the force being applied, and this deformation can cause a slight motion in the direction of the force being applied. Okay, so what you have is v dot f, okay, is not 0 now. V dot f is not 0 in this direction. Okay, let's take one particular case and try to understand what happens here. Let's say that there is a robot applying some force to a surface, and this surface is stiff. It has some stiffness k. So the force being applied is going to cause some amount of deflection, and the force and the deflection are related by Fs kx. Okay, and the change in potential energy is the integral of the velocity into the force. So velocity was x dot and the force is kx. So this entire thing, the integral from 0 to t, would turn out to be half of x of t square minus half of x of 0 square, the total motion if it is taken. Okay, so the the change in potential energy is so much, and if you have a higher value of k, it takes more energy to cause this change in position. Okay, if you want the same x of t starting from x of 0, as k increases, the amount of energy required to do that action also increases, which means that the higher value of k, the more the environment is impeding the motion of the end effector. Okay, and this relationship between the force that is being applied and the motion that is being obtained is captured by something, a term that is called as the mechanical impedance of your manipulator or of your environment also. Okay, and you can use networks, the electrical networks or mechanical networks, to actually model the this interaction between the robot and the environment. Okay, and the type of network that you would typically use are one port networks. So there would a typical one port network would have two types of variables, something that are called as across or effort variables, and something called as flow or through variables. Okay, and and in both mechanical and electrical cases, you have an equivalence for this. So if you have a mechanical system, then the effort is the force that is being applied, and the flow variable is the velocity that is being achieved by the application of the force. Okay, and in case of, and now let us see this case of, in this case you have a mass, you have a damper, and you have a spring. Okay, so the mass is going to affect the derivative of the velocity. So mass affects the derivative of the velocity. The damping depends, the amount of force that is in the damping, that depends upon the velocity itself. And in the case of the spring, the force that a spring will exert depends upon the integral of the velocity. Okay, so you have this being something that exerts a force proportional to the derivative of the term of the flow variable, the damping, the flow variable itself, and the spring, a the integral of the flow variable. Okay, now when you come to the electrical equivalence, you have the voltage being the effort variable, and the flow being the current being the flow variable. Okay, here again, if you take if you take this force, and the inductor here is going to affect the derivative of the current. The resistor gives the current itself, and the capacitor is integral of the current. Okay, so you have something that is very similar in happening in these two cases, and so you can use the concept of the electrical counterparts to work out what happens in the mechanical system and vice versa. Okay, so and in the electrical counterpart, you have the concept of one port networks, and you can use one port networks to analyze the interaction between the environment and the robot. And something else that needs to be seen is that the product of the through and across variable, that is, in the case of electricity, it is V is, V is the across variable and I is the through variable, or so V dot I is instantaneous power. Similarly, F dot V is also instantaneous power. Okay, and energy dissipated is actually the integral of V dot F, that we have actually seen in the case of that earlier case where you have a stiff environment, an environment with a finite amount of stiffness. Now the interaction between the robot and the environment can be seen as a connection of these two one port networks, and in a sense the energy exchange between these two networks is also the energy exchange between the robot and the environment. Okay, now you have something called as an impedance operator, which gives a relationship between the effort and the flow variable. So if you take the example of the one port network, you have the impedance Z of S defined as a ratio between the Laplace transform of the effort variable, that is, in case of an electrical network, that will be the velocity, not the velocity, V being the voltage, and the Laplace transform of the force variable, sorry, the effort, yeah, Laplace transform of the flow variable and the Laplace transform of the effort variable. Okay, here it's V of V is the voltage or I is the current. Okay, and that is actually very confusing. So let me restart it. In case of a one-port network, the impedance Z of S is defined as the ratio of the Laplace transform of the effort variable to the Laplace transform of the flow variable. That is Z of S is F of S by V of S. Now, in case of an electrical network, this would be the Laplace transform of the current I by V, I of S by V of S. But let's not get confused by this notation of V being repeated. Let's keep it as F by V. That is easier. Okay, where F is the flow variable and V is the effort variable. Okay. Effort variable. Now, if you say that if you take the example of a spring mass damper system, now what you have here, the mass, as I said, was affecting the derivative of your flow variable, that was velocity. So you have m into s, where s is indicative the Laplace transform of a derivative operation. The damper was actually, the damping force was just proportional to the velocity itself, and k by s, that means that the spring constant gave a force which was proportional to the integral of your velocity. So you have the impedance function being the ratio of the effort variable F, okay, to the flow variable. Okay, so that is Z of S will have this expression in case of a spring mass damper system. Now, depending upon the low frequency or the DC sort of response, the impedance operators can be classified. Okay, the impedance Z of S, okay, in a Laplace, in terms of the Laplace variable S, this is said to be inertial if Z of S as S tends to 0 becomes 0. Okay, then it is an inertial one, inertial impedance. Okay, on the other hand, if Z of 0 is a constant and a finite constant, then it's a resistive impedance operator, and it is said to be capacitive if it becomes infinity as S goes to 0. Okay, so if you go back to the previous slide, if you take the mass, the damper and the spring constant separately, for the mass, so you have mass becomes ms in terms of the Laplace, the damper becomes b, and the spring gives k by s. Now if S tends to 0, this becomes 0, this becomes a constant B which is finite, and this tends to infinity. So the mass is inertial, this damper is resistive, and this spring is capacitive impedance in this case. Okay, so as I said this thing, so a mass just staying, a mass with a force acting on it and moving on a frictional surface will be an inertial one. A mass moving in a viscous medium will have a resistive component B, okay, in addition to the inertial component Ms, okay, and a spring with a linear spring with some stiffness K will have a impedance function of K by S, so, and it is capacitive. Okay, now let's see that, since in the earlier case in the last class we had seen about how the joint torques and the end effector, not the joint, but the joint positions and the end effector position, the task space and joint space positions and velocities, how they are related, and how we can translate task space specifications into joint space specifications so that a appropriate torque can be applied. Now in here, what you have here is that you have forces being experienced by the end effector due to the interaction with the environment, and you have a vector of joint torques also, tau. Okay, you have tau and you have forces being experienced by the end effector. Now this force, let us say this force F produces a virtual displacement delta x in the end effector. Okay, and so this is in task space. Okay, and of course in the joint space also there is a deflection. Okay, so the task space and the joint space deflection are what you call related by delta x is j of q delta q. Okay, now the virtual work done is the difference of this. F transpose delta q is the virtual work done by the environment, okay, and by having a deflection in task space, and tau transpose q is the work done by the manipulator. Now substituting delta x as j q of delta q, you have delta w to be this expression. However, and once you say that once the system is in equilibrium, then this delta w would be equal to 0 when the manipulator reaches equilibrium. Okay, so what you have is delta w is F transpose j delta t tau transpose into delta q. Okay, however, the coordinate frame that is being chosen to define tau or to define q is immaterial, because this should be same irrespective of what I choose as the coordinates of q. Okay, so that would mean that this equality should be satisfied always, and tau should be j of q transpose. Actually this should be j transpose q, really this should be equal to tau. Okay, now in addition to whatever was there in the original dynamical equation for a manipulator, you have this additional term j transpose Fe, that is the force that is acting in the joint space of the manipulator. Okay, that is this additional force tau that is acting on the joint space because of the environmental interaction. Okay, so that should be added to the dynamics now. Okay, so once this is added to the dynamics, okay, then you can as the case that we had done with the inverse dynamics control, you can say that this is the actual force, that is Fe is the actual force interaction, okay, and AF is desired interaction. Okay, so and you can and as the earlier case, you have AQ being the desired acceleration. Okay, and we can also use the relationship between the joint space and the task space velocities and get it into that AX, the desired acceleration in the task space, is just this, which we have seen also in the last class. Okay, now when you substitute these two equations, when you substitute this equation, you end up with the actual acceleration in the task space is the desired task space acceleration plus some term that depends upon the force, the desired end effector force and the desired interactive force with the environment and the actual force with the environment. Okay, where this WQ is derived from the Jacobian and the mass matrix, and it's called as the mobility tensor. Okay, so if we are able to say or able to assure that AX, the desired joints task space acceleration, is a function of only of position and velocity, and the desired force AF is function only of forces, it is not a function of the either the task space coordinates or the joint space coordinates, then you can decouple these two terms. Okay, in addition, if you assume that AF is FE, this term just disappears also. Okay, and the task space just becomes a double integrator system, x dot equal to the task space dynamics becomes a double integrator system, x dot equal x double dot is AX. Okay, now let's take a small example of what is happening in this impedance control. Okay, and let us say that you have a system that is experiencing an external force F, and you are applying a force U. Now they are in the opposite direction, so the effective acceleration that is happening is mx dot is U minus F if I take x along the direction of U. Okay, now when U is equal to 0, with respect from the force, the environment, that is whatever is applying this force, for it it appears as a mass m. So you will have m x double dot is minus F. So for this force, x double dot appears as a mass, the mass actually appears as a pure inertia of mass m. Okay, the block appears as a pure inertia of mass m. However, when you use U is equal to minus mf, where this small m is some constant that we are assuming, and F is the force that is being applied. So this uses a force feedback. Okay, the environmental force is detected by some force sensor, and that is fed back. So now in this case, you have mx double dot is minus 1 plus m times f. Okay, so now apparently this looks as if the inertia of the system has decreased. Okay, it looks as if the inertia of the system has decreased. So the impedance of the system, impedance of the whatever object is there, that can be modified by an appropriate force feedback. Okay, in this case it is changing the inertia of the system. Now in impedance control, you regulate the mechanical impedance by applying an appropriate force feedback. Okay, what you do is that you formulate the impedance control in the standard inner loop outer loop architecture. Okay, the inner loop will of course be a nonlinear one that works on the joint space. Okay, and the outer loop will be a linear control that works on your force feedback or the task space dynamics also. Now in the earlier example, if you set ax, so you have x double dot is equal to ax, that was what we ended up with. Okay, so if you set up the dynamics or the desired acceleration as xd double dot minus this expression, where md, bd, kd and fe are what we desire. Okay, fe is actually the force feedback that we desired. So what we end up with is this situation. Okay, the closed loop dynamics of the system, the closed loop system would have the desired impedance properties. Okay, and so now fe is ze of s by ve of s. So you would end up with ze being equal to 1 by something, being dependent on this value. Okay, and now the problem with this is that this achieves only one of the objectives. That is, you have now, instead of having a single objective case where there was only position control till now in the earlier lectures, here you have position control and force feedback also, or force control also. So these both, when you use the pure impedance control, only the force control may be achieved. The position control may not be, there may be position errors also. So you can use a more involved concept of a hybrid impedance control, where you can say that both the position error can be made to 0 and the force can also be applied. Okay, this looks very similar to the case of, because we are talking about a non-zero error, the solution, the hybrid control is applicable whenever your system, your environment naturally has an integrator in it. So a natural integrator in the environment would mean that the steady state error will go to 0, like the adding of the I component in a PID controller. Okay, this natural integrator is going to ensure steady state equal to 0 in addition to the force, the desired force Fe being applied. Okay, now if you go back and see which of the three impedance environments had the property, has an integrator in it, you see that the capacitive environment had an integrator in it. So you can say that if you have a capacitive environment, then you can assure that the steady state value can be made to go to 0 by choosing an appropriate control, impedance based control. Okay, so with that, we come to the end of this lecture. As I had mentioned, that you just need to have a basic idea of all these concepts. Uh, very, and with that, I would say thank you.